So before I took on the director role, I actually had time to think about scientific questions in more detail. So this talk will really be summarizing a passion project of mine that I worked over the last several years, really, looking at the thermal evolution of the Yilgarn craton and the implications that has on the magmatic history, the Archean cratonisation, and potentially in mineralization as well. Okay, so all of the work that I'm going to be talking about today has recently been published in an open access article in the journal Geology. So this is freely available. So if you want to look at any of this stuff in more detail, it is there for you. But jumping to the conclusions, what this work shows is that the redistribution of Archean mass and heat was largely internally driven through high radiogenic heat production, and that elevated temperatures within the crust were likely sustained for at least 150 million years, if not longer. Okay, so essentially what I'm going to do is just walk you through the 4 figures in this paper. And if you're familiar with geology papers, 1 figure is usually about 5 figures. So I'll try to do this in a quick way. So the Yilgarn, of course, has been a very important area of work for us for several decades. So we have an extensive, high-quality craton-wide data sets to work with. So this figure on the right summarizes the key data sets that were used in this work. Obviously, the interpreted bedrock geology, which is the base map on this figure, is very important. The little gray circles are geochemical data points. These are the ones shown on this figure are felsic granite compositions, but there were thousands of other lithologies that were included in this work that aren't shown on this map. A lot of those geochemistry points have geochronology and isotope information attached to them, which tells us about the age, but also the sources that these rocks were derived from. The red lines are the active 2D seismic lines that were used in this work to constrain crustal architecture. And then the colorful circles, which you saw in Raf's talk, are the metamorphic data points that tell us a lot about the pressures and temperatures of metamorphism, which tells us the thermal structure of the crust at that time. Okay, so I'm now going to focus a bit on what the geochemistry tells us. So this plot here is a plot of different lithologies considered in this work, plotted against their heat production that's calculated from the concentration of heat-producing elements, which are potassium, uranium, and thorium. And what's also shown, the gray bar is the global granite average, which has a heat production of about 2.5 microwatts per cubic meter. And the pink bar is the Yilgarn felsic average, which was previously estimated in an older study. And what we can see is that the lithologies in A, those are all the high calcium granite types, have radiogenic or heat production values that are about average. But what we can also see is that the B and C rock types, which are the different types of low calcium granites, are quite radiogenic. So these are these are elevated values. And then the other rock types, which are mainly mafic lithologies and different components of the greenstone belts, are pretty unradiogenic, which is what we would expect. Now, because heat production is because of radioactive decay, these modern day values are going to be minimums. So if we look at what this might have looked like back at 2640 MA, which is of course a very important time in the evolution of the Yilgarn, not surprisingly, all of these rock types have more elevated heat production values as compared to the modern day. But what's really striking is those red and green boxes, the low calcium granites, these are starting to get crazy radiogenic. It's not used in the paper, but these are extremely elevated in their heat production. Okay, we can look at this in a different way. So this figure shows it's a bit hard to see, but it's the crystallization age of dated granites versus, again, their calculated heat production. And with these averages shown in the little gray and pink bars, and 2 things fall out from this. The first is that compared to the averages, there is evidence for high heat production as far back as 300 MA, 3000 MA, 3 billion years ago. And then we also see a progressive increase in heat production, really kicking off at about 2.8, but certainly by 2.7, where the low calcium granites in pink in particular, again, are getting extremely radiogenic. Okay, we can look at this data in another way. So this is a contour map of the present day surface heat production. So it's, again, just those heat production values now contoured. And anything lighter or brighter than the darkest green are, again, higher than average values. What's also shown on this map are, in the blue crosses are the surface heat flow measurements that are available for the Yilgarn. And that's essentially the last gasp of heat that's coming out of the crust. And that is a function of the integrated heat production throughout the entire crustal column. Okay, this isn't just a surface feature. This is the heat that's coming out because of all that heat production you have in the crust. I'll come back to that. Okay, and then again, we can do the same sort of exercise for the Archean heat production at 2640. And really, what really starts to fall out from this is just how radiogenic the now exposed crustal level of the Yilgarn would have been. So this is telling us something pretty fundamental. So two really important questions fall out from this. First is, what was the distribution of these heat-producing elements through the crust with time? And importantly, what were the thermal effects of that? So to investigate this, we did some simple 1D thermal models. This is the present day setup for the first model, just to step you through what these things kind of look like. The first thing we need to do these models is a sense of the crustal architecture. So we need crustal layers, we need to know things about them and their depths. We need to have a lithosphere thickness. So for the modern day, this was estimated at 225 kilometers, which is consistent with published values. The top of the model was fixed at 10 degrees Celsius, and the bottom of the model, which is the LAB boundary, for the modern day was fixed at 1300 degrees. Now I did some sensitivity testing on this, so if that varies by 100 degrees, it actually doesn't change the thermal structure that we see in the crust. So even though this value is uncertain, especially as we go through time, it actually doesn't really matter. Okay, so zooming in on what the crustal architecture looks like in the present day, this is largely based on the seismic interpretations that we have. And in terms of the petrogenetic models that we have for these rock types, that really comes from our zircon geochronology and isotope information. And so at the present day, we've got a thin upper crust of dominantly low calcium granites with a bit of greenstone, underlain by transitional TTGs, or the high calcium granites. And then we have what's called the Archean seismic province, which is an unexposed, very thick package within the mid to lower crust, or the mid crust really, that is completely unexposed. So we actually don't know anything about what that unit is. And then a mafic lower crust and a lithospheric mantle. I realize I did forget to say something quite important, so I'm just going to go back here. Okay, so just coming back to this figure, I did want to point out that this is quite a West Yilgarn focused data set. I acknowledge that. That really was the focus of the work. But we've heard through several talks today, JT, Raf, Matthew, who just spoke, that both the West Yilgarn and the Eastern Goldfields do share a common geological history. And so I do think the results from this work has some important implications on the goldfields, and I'll touch more about that at the end. But I did just want to emphasize that. So this shows the calculated, or the heat production values that were used in the model. And all the ones in red were based on the geochemical data set. So these are real values derived from thousands of data points. Importantly, the Archean seismic province is a significant unknown. We have no information about this. Well, we do have those surface heat flow measurements. And so this was a great way to figure out what the heat production value of this unexposed unit that we know nothing about may have been. And so the best fit to match what we see at the surface heat flow with what the model predicts tells us that a good chemical proxy for the Archean seismic province was a sodic diorite. So this is what I used in terms of a composition in all the subsequent models. I'm not saying it is a sodic diorite, but compositionally, especially in terms of its heat production, its heat producing elements, this was the best proxy to match what we see in terms of the surface heat flow. It's very handy to have that data. So this was the full model setup. So we've got the present day configuration on the right, which is what I've just stepped you through. That was mainly really helpful for determining what this unexposed unit 3, the Archean, may have been. And then we looked at 3 different time slices from 2.9 to 2.6. Now this is obviously quite a simplified snapshot of the evolution of the Yilgarn. And that was somewhat by design, because by having fairly simple time slices, it kind of keeps us more connected fundamentally to the data sets. We add more complexity, we add more assumptions, we add more uncertainties. So what we have in the first model is a time slice from 2.9 to 2760, and that's essentially composed of a greenstone upper crust, a high calcium, underlain by high calcium granites, and then the Archean, the mafic lower crust, and the lithospheric mantle. In the next model, Model 2, which is appropriate from 2760 to 2650, we now have a thicker package of greenstones, underlain, and then the emplacement of transitional TTGs. And we know that those rocks, this unit 6 in Model 2, was derived from the underlying high calcium granites, the TTGs, and the mafic lower crust. And then we get into a really interesting time slice between 2650 and 2600, which is when we have the granite bloom that we see across the Yilgarn. We've got a granite greenstone upper crust, the emplacement of low calcium granites, which again are these radiogenic granites, which we know are derived from the underlying transitional TTGs and the Archean. Okay, I'm not going to spend a lot of time on this figure. This now shows all of the heat production values that were used in the model. The paper goes into this if you want to know, and I'd be happy to elaborate in person. But what I want to emphasize is that a lot of thought went into each one of these values. And importantly, the numbers in red are actually adjusted to account for the extraction of the heat-producing elements to create the products derived from those sources. So we took into account a mass balance, essentially, of heat production to keep an internally consistent model that made geological sense. So finally, some results. So this figure on the right shows the predicted geotherms for each of the models. So in black, we have the present-day model. It's quite cold. It's what we would expect, which is not surprising, because we use the surface heat flow to essentially, fix. It was an important constraint in deriving some of the unknown heat production. So that should give us a sensible value. What's shown in blue and green are quite hard to differentiate, but those are models 1 and 2, and they are remarkably similar. So even though we are starting to move heat production through the crust or heat-producing elements, those geotherms are actually quite similar. The red line is the predicted geotherm for Model 3, so kind of this last gasp of the Yilgarn's evolution, and you can see that geotherm is now starting to cool. And that is essentially what's happening as all those heat-producing elements are now starting to go into the low calcium granites, this layer 5. That is effectively starting to cool the crust, which is what's driving the cratonisation. What I also have on this figure in the light, thinner gray lines are geotherms that were previously published for the Eastern Goldfields from Bojorquez and Sandiford in 2006. And you can see that their values are showing slightly cooler geotherms. I'm going to come back to that. I'm not going to talk about their work in detail, but I'm going to come back to that concept. Okay, so now coming back to the metamorphic data set, these are great rocks to have because they give us a snapshot into the thermal evolution or the thermal structure of the crust. Okay, and so what's plotted here are the metamorphic data points, basically as their pressure or depth as you go down the y-axis and temperatures increasing from left to right. And we can see that the geotherms, particularly the blue and the green ones, so more appropriate for the older part of the story, are capturing some of the metamorphic data points, which is nice to see. But a lot of those metamorphic data points are suggesting that there were hotter conditions in the crust at that time. Okay, if we consider now the thermal effects of the emplacement of contemporaneous granites, we start to capture that metamorphic data. So we know there's a lot of magmatism happening between 2650 and 2600. Well, it turns out that the temperatures associated with that granite emplacement really does seem to capture that metamorphic record. Okay, so what that's telling us is, yes, the thermal effect of granites, at least in the later part of the evolution of the Yilgarn, in the mid to upper crust, was important. And this is consistent with the regional contact metamorphic story, which of course has been been proposed by others, but I don't think it's been demonstrated in this way. Okay, so that's all well and good. We know we've got granites causing some metamorphism, but what is causing the granites? What is driving crustal melting? Well, we can look at this by looking at where these predicted geotherms start to cross some of the major melt-producing reactions. And so what's shown on here, again, are the geotherms, a bit faded now. I also have on here the tonalite wet solidus in blue, the biotite dehydration melting in brown, and the amphibolite solidus in green. And yes, we can see that each of these geotherms does cross these melt-producing reactions somewhere in the crust. Well, we can look at this a little bit more meaningfully. So this shows the crustal architecture that we used for Model 2 with the predicted geotherms. And we can see that the tonalite wet solidus is crossed at about 20 kilometers, and both the biotite dehydration melting and the amphibolite solidus are crossed slightly deeper. So this tells us that crustal melting can occur simply through radiogenic heating. Now, if we look at Model 3, again, this last part of the Yilgarn's evolution, looking at the red line, we see that it crosses the melt-producing reactions in the lower parts or the mid-crust. But if we now look at that dashed geotherm, so the geotherm that takes into account the granites that were kicking around as well, well, wow, we're really starting to cross the melt-producing reactions at much shallower levels. And interestingly, if you're looking at that melt reaction 2, the biotite dehydration melting, we're starting to cross that at 10-kilometer depth. So this is entirely consistent with the model that Hugh was talking about the formation of these lithium-bearing leucogranites. This is consistent with biotite dehydration melting at very shallow levels. So thank you for that whirlwind. To conclude, this work shows that the Yilgarn crust was more radiogenic or is more radiogenic than previously recognized. Radiogenic heat thermally primed the crust for melting and elevated temperatures by at least 150 million years. Notably, if there's another external heat source, so if we consider mantle, any sort of mantle input, mantle underplating, mafic magmatism, a plume, that's only going to promote melting at even shallower and shallower levels. So this is kind of a minimum story that I'm presenting. The metamorphic record that we see suggests both radiogenic heat and magmatism played an important role. And this, of course, has implications for mineral systems. So I've touched on the lithium mineralization, but I also open up what I talked about this morning about natural hydrogen potential. We know that radiogenic rocks, particularly in very old terrains, can actually, in fact, help produce natural hydrogen. I'm going to finish this talk ending with a question, and that is, could the Eastern Goldfields superterrane actually be cooler? That is certainly what Simon and Bedorkis and Sandiford's work suggested. We are looking at potentially cooler conditions. Does this explain potential differences in mineral endowment between the two different terrains? I can't answer that. I think it's a great question and certainly something worth exploring. So we should do that. Thank you.